Tonight, we're going to examine one of the most persistent and most consequential misconceptions in the public understanding of space travel. It is the idea that going to space means going up, figuratively, literally. The assumption that getting to orbit, reaching the moon, exploring the solar system, is primarily a problem of altitude, of gaining sufficient height above the surface that you are no longer in the atmosphere, and therefore in space. The image in almost every depiction of space travel, the rocket rising majestically upward, the astronaut floating above the clouds, the spacecraft ascending toward the stars, encodes this idea so thoroughly that it rarely gets questioned. It is wrong, or, more precisely, it is so incomplete that being wrong is the charitable interpretation. Height alone does not get you to orbit. Going straight up at any speed does not place you in orbit. Spacecraft that ascended to the altitude of the International Space Station by going directly upward and then stopped thrusting would fall straight back to Earth, arriving roughly as dramatically as it left. The ISS is not in space because it is 400 kilometers above the surface. It is in space because it is moving sideways at approximately 766 kilometers per second, fast enough that the rate at which it falls toward Earth exactly matches the rate at which the curvature of Earth's surface curves away beneath it. It is falling continuously. It is missing the Earth continuously. That is orbit. The confusion between altitude and orbital motion is not trivial. It produces fundamental misunderstandings about the energy requirements for space travel, the trajectory of rockets, the meaning of microgravity, difficulty of sending humans beyond low Earth orbit, and the basic question of what it would actually mean to leave Earth permanently. Someone who understands why we never simply fly up understands the fundamental physics of orbital mechanics, and through that understand why space travel is hard in the specific ways it is hard rather than the ways that visual intuition suggests. The story of Up is also a story about the human body's hardwired certainties and how poorly they generalize beyond the surface of the planet that shaped them. The vestibular system in your inner ear, the proprioceptive signals from your joints and muscles, and the gravitational tug you have experienced every second of your life have jointly constructed a sense of orientation so automatic and so absolute that it feels like information about the universe rather than what it actually is. Information about your relationship to one particular planet's gravitational field. Take that field away, and the sense of up goes with it. The universe does not have an up direction. The universe has gravity, and gravity defines local up for anything with mass nearby. But there is no cosmic up, no preferred orientation, no direction in which the universe thins out and another begins. By the end of tonight, you will understand why rockets do what they actually do, why orbit is fundamentally about velocity rather than altitude, why there is no meaningful up direction in interplanetary space, what the physical requirements of going somewhere beyond Earth actually are, and why the visual vocabulary of space travel as vertical ascent is one of the most misleading intuitions that popular science education has failed to fully correct. If this kind of honest, physics-first examination of what space travel actually requires is what you want, subscribe and leave a like. It helps this channel find people who want the real version. Now, let's begin with what up actually means, the specific physics that produces this counterintuitive situation is not exotic or new. It was worked out by Isaac Newton in the 17th century. extended by the orbital mechanics discoveries of the 18th and 19th centuries, and operationalized by the engineers who built the first orbital rockets in the 1950s. Every launch team, every mission controller, every navigation engineer who has ever worked in spaceflight understands this picture clearly. The public understanding of spaceflight, shaped overwhelmingly by images of vertical ascent and by the language of going up and coming down, has largely missed it. This gap between how space travel works and how it is commonly imagined is not merely an aesthetic failure. It produces systematic errors in how people think about the difficulty of space travel, the meaning of weightlessness, the engineering of rockets, and the long-term prospect of humans leaving Earth. Someone who thinks getting to orbit is primarily about going high enough will have a completely wrong model of why rockets are so expensive, why the energy requirements are what they are, and why certain things that seem easy, flying an airplane high enough or firing a very powerful gun straight up, do not constitute getting to space in any meaningful sense. The word up, for any human standing on Earth's surface, means one and only one thing in its fundamental physical sense: away from the center of Earth in the direction that opposes gravitational acceleration. This definition is so obvious as to seem not worth stating, but unpacking it reveals several things about up that are far from obvious. First, up is local. Direction in Tokyo is not the same geometric direction in space as up in Sao Paulo. The two directions, if extended outward from Earth's surface, verge by roughly 230 degrees, because Tokyo and Sao Paulo are on nearly opposite sides of the globe. A person in Tokyo standing perfectly upright and a person in Sao Paulo, still perfectly upright, are in fact pointing in nearly opposite directions in any coordinate system that doesn't use Earth itself as the reference. It is defined by gravity, and gravity on a roughly spherical body points toward the center from every surface point simultaneously, producing a different up direction at every location. This is why the early conception of a spherical Earth was so philosophically difficult for people to accept even once the geometric evidence was clear. If Earth is a sphere, people on the other side of it must be upside down. The resolution of this puzzle is that up is not a direction in space, but a relationship to a gravitational field. People on the other side are not upside down, have a different up, defined by the same gravitational field pointing toward the same center. Second, up on Earth is not constant. Earth is not perfectly spherical. It is oblate, bulging at the equator due to its rotation, with an equatorial radius of 6,378 kilometers and a polar radius of 6,357 kilometers, a difference of about 21 kilometers. The surface gravity is correspondingly not constant. It is slightly weaker at the equator, roughly 9.78 meters per second squared, and slightly stronger at the poles, roughly 9.83 meters per second squared. Local topography, underground density variations, and the presence of large mountain ranges all slightly perturb the local gravitational field. Direction your plumb bob hangs when you let it drop is the actual local definition of straight down, and it varies measurably across Earth's surface. Third, and most importantly for tonight's topic, in the context of Earth's surface, is a surface-centric concept that becomes progressively less useful and eventually meaningless as you move away from that surface. The altitude of the International Space Station, 400 kilometers above the surface, the direction toward Earth's center is still well defined, and gravity is still significant, roughly 88% of its surface value. But the relevance of that direction depends entirely on what you are doing. If you are in a spacecraft moving at orbital velocity, direction is continuously changing. Since you are orbiting, Earth's center rotates around you once every 90 minutes, meaning up as defined by gravity is pointing in a different direction every moment. Absolute direction of up at orbital altitude has no physical significance for the astronaut in orbit. They feel no acceleration toward or away from Earth because they are in free fall. The word up, therefore, describes three overlapping but distinct things: the direction of gravitational acceleration at a given point, the direction of perceived weight for an observer, and a culturally inherited intuition about the vertical. All three of these come apart in space, and understanding why they come apart is the foundation of understanding why space travel looks the way it does. The GPS system provides a practical illustration of how seriously up varies across Earth's surface. Every GPS satellite transmits a precisely timed signal, and receivers on the ground calculate their position by measuring the time delays between signals from multiple satellites. But the system's accuracy depends on knowing with extraordinary precision where each satellite is. The satellites orbit in medium Earth orbit at roughly 20,200 kilometers altitude, and their orbital parameters must be continuously updated. Calculation of those parameters requires a model of Earth's gravitational field that accounts for the geoid, the equipotential surface corresponding to average sea level, which differs from a perfect sphere by tens of meters in various regions. The GPS system's accuracy, which is better than a meter for civilian use and centimeter level for military and scientific applications, depends on correctly modeling this variable gravitational field rather than treating Earth as a uniform sphere. This seemingly technical detail reinforces the fundamental point. On Earth is not a simple or uniform concept even at the surface. It varies continuously, measurably, and in ways that matter for precision applications. When we extend the concept of up beyond Earth's surface into space, the variations and complications only multiply. Kármán line at 100 kilometers above sea level is conventionally designated as the boundary between Earth's atmosphere and outer space. It was proposed by the Hungarian-American engineer Theodor von Kármán in the 1950s as an approximate threshold above which aerodynamic lift becomes essentially impossible, because the atmosphere is so thin that any vehicle moving fast enough to generate sufficient lift would already be exceeding orbital velocity. The line is not a physical boundary in any sharp sense. The atmosphere does not end at 100 kilometers, and space does not begin there. It is a useful administrative and legal definition adopted by international bodies, including the Fédération Aéronautique Internationale for awarding astronaut wings, and by the Outer Space Treaty for establishing where national sovereignty ends and international space law begins. What the Kármán line does not represent is the destination of orbital space travel. Someone who crossed the Kármán line and stopped, hovering motionless at 100 kilometers altitude, would not be in orbit. They would immediately begin falling back to Earth under the influence of gravity, which at that altitude is approximately 97.5% as strong as at the surface. The fall would take roughly 4 to 5 minutes to return them to the surface, on a trajectory that would become increasingly dangerous as the thickening atmosphere converted their kinetic energy into heat. The confusion between the Kármán line as a definition of space and the Kármán line as a destination for space travel was vividly illustrated by the suborbital flights of the new commercial space companies in the 2010s and 2020s. Blue Origin's New Shepard rocket and Virgin Galactic's Spaceship Two both carried passengers to altitudes above 100 kilometers. Qualifying them as astronauts by the FAA's definition at the time, neither vehicle was capable of reaching orbit. They went up and came back down, following ballistic trajectories. They were in space in the definitional sense. They were above the Kármán line. They were not in orbit. The passengers experienced a few minutes of weightlessness at the top of their trajectory, and then returned to Earth. Reaching the Kármán line with the intention of staying requires not altitude, but velocity. The difference between a suborbital hop that crosses 100 kilometers and a genuine orbital mission is roughly 7.6 kilometers per second of horizontal velocity, which represents the large majority of the energy budget of any orbital launch. Altitude is almost a footnote. The massive, expensive rockets that carry crew and cargo to the International Space Station are not struggling against the pull of gravity as they climb upward, primarily accelerating sideways to the enormous horizontal velocity required for orbit. Climb to 400 kilometers requires only a small fraction of the energy that the horizontal acceleration to 7.66 kilometers per second demands. This is the first critical realization in understanding why we never simply fly up. The problem of getting to orbit is not the problem of going high enough. It is the problem of going fast enough, sideways. Commercial suborbital flights of the 2020s have created an interesting cultural moment where the Kármán line has been repeatedly crossed by private customers who are genuinely in space by the internationally accepted definition, but who are having an experience that has almost nothing in common with orbital spaceflight beyond the 15-minute window of weightlessness at the apex. The difference in engineering complexity, propellant requirements, and physical demands on the vehicle between a suborbital hop and orbital insertion is enormous. A suborbital trajectory to 100 kilometers altitude requires roughly 1 to 1.5 kilometer suns of delta V from the surface. Reaching low Earth orbit requires roughly 9 to 10 kilometer suns. The energy scales with velocity squared, so orbital insertion requires roughly 40 to 60 times as much energy as the suborbital trajectory. Reusable suborbital vehicles like New Shepard can complete a mission and land their booster within minutes. Orbital class rockets require far more elaborate staging, hardware being orders of magnitude more stressed by both the propellant requirements and the aerodynamic and thermal loads of high-velocity flight. Passengers in suborbital vehicles experience one continuous arc of flight. Orbital crew members experience the continuous mechanical and physiological demands of microgravity for however long their mission lasts, from days to months. If you have watched a rocket launch in real time, either live or in video footage, you may have noticed something that seems slightly counterintuitive in the first minutes of flight. The rocket rises vertically for perhaps the first 10 to 15 seconds, then begins to tilt, not dramatically at first, but unmistakably. Within a minute or two, large rockets are traveling nearly horizontally rather than vertically. By the time the main engines cut off and the spacecraft reaches its target altitude, the vehicle is moving almost entirely parallel to Earth's surface, rather than perpendicular to it. This maneuver is called the gravity turn, or the pitch-over maneuver, and it is not an error or a compromise. It is the entire point. The vehicle is not trying to go up. It is trying to go sideways at enormous speed, and going straight up would be a waste of propellant. Every second the rocket spends accelerating vertically is a second of propellant consumed fighting gravity directly downward, rather than building the horizontal velocity that actually enables orbit. The math is unambiguous. The International Space Station orbits at an altitude of approximately 400 to 410 kilometers. Gravitational potential energy difference between Earth's surface and 400 kilometers altitude is relatively small. Converting this potential energy requirement to equivalent propellant, it represents only a few % of the total fuel required for an orbital launch. The rest is going into kinetic energy, the energy required to accelerate the spacecraft to orbital velocity. Roughly 90 to 95% of the energy in an orbital launch is spent gaining speed, not gaining altitude. The gravity turn begins essentially at the moment of liftoff. In the first few seconds, the rocket rises vertically to clear the launch tower and to allow the vehicle's control systems to establish vertical orientation. Then, using the gyroscopic properties of its spinning guidance instruments and the thrust vector control of its engines, the vehicle begins to pitch over, tilting its nose in the direction of the target orbit. From this point forward, the thrust is being directed increasingly horizontally, and gravity is doing the work of pulling the vehicle into a trajectory that curves with the curvature of Earth's surface. The atmosphere plays a role in the shape of the gravity turn as well. In the dense lower atmosphere, the aerodynamic forces on the rocket are large, and flying at high angles of attack, meaning with the nose pointed far off the direction of travel, creates structural stresses that can destroy the vehicle. The gravity turn is therefore designed to keep the angle of attack near zero throughout the powered ascent, meaning the nose is pointed very close to the direction of motion at every moment. The atmosphere thins and aerodynamic forces decrease, the vehicle can adopt more aggressive horizontal orientations. The pitch program, the specific timing and rate of the pitch over maneuver, is calculated before launch and is a precisely timed sequence of attitude adjustments. The vehicle's guidance computer, receiving accelerometer and gyroscope data, follows this pre-calculated pitch program while simultaneously responding to any deviations from the planned trajectory caused by wind, atmospheric density variations, or other disturbances. The result is a trajectory that follows the planned path to within fractions of a degree in attitude and fractions of a meter per second in velocity at any given point. The visual impression for observers at the launch site is sometimes surprising the first time they see it. The rocket, which rises vertically and impressively for those first few seconds, seems to fall over onto its side surprisingly quickly, especially for the largest rockets, where the scale makes the maneuver seem more dramatic. What is actually happening is that the rocket is doing exactly what it is supposed to do, executing the pitch program that will deliver the payload to orbital velocity most efficiently. The vertical phase is brief, not because rockets are underpowered for vertical flight, but because vertical flight is the least efficient way to spend propellant given the orbital mission objective. The staging events that occur during the ascent, when spent propellant tanks and engines are jettisoned to reduce the mass the continuing engines must accelerate, also occur primarily during the horizontal acceleration phase rather than the vertical phase. By the time of most staging events, the vehicle is moving substantially faster horizontally than vertically. The specific number that defines orbit at the altitude of the International Space Station is 7.66 kilometers per second. This is 27,576 kilometers per hour, or approximately 17,138 miles per hour. It is a speed so far beyond ordinary experience that comparison is difficult, but a few frames of reference help convey the magnitude. The fastest crewed aircraft ever built, the North American X-15 rocket plane, reached a top speed of approximately 7,274 kilometers per hour in its 1967 record flight. International Space Station moves at almost exactly 4 times that speed. The fastest conventional rifle bullet travels at roughly 3 to 4 kilometers per second. ISS moves at roughly twice that. It crosses the entire continental United States in approximately 10 minutes. This velocity is not chosen arbitrarily. It is the precise speed at which the centripetal acceleration required to follow a circular path at the ISS's altitude exactly equals the gravitational acceleration pulling the station toward Earth's center. 7.66 kilometers sescons at 400 kilometers altitude. The centripetal acceleration needed to curve around Earth equals approximately 8.7 meters per second squared, which is the gravitational acceleration at that altitude. The station is always curving toward Earth at exactly the rate that Earth's surface curves away from it. This is the geometric definition of orbit, increasing the speed above 766 kilometers seconds would cause the orbit to rise. The station would trace a higher arc, moving to a larger elliptical orbit. Decreasing the speed would cause the orbit to lower, directionally, in that intersecting Earth's surface. The relationship between orbital altitude and orbital velocity is fixed by Newton's law of gravity and the geometry of circular motion. There is no way to stay at 400 kilometers altitude without moving at approximately 7.66 kilometers seconds. Slower than that, and you fall. The orbital speed for lower altitudes is higher. A spacecraft at 200 kilometers altitude needs about 7.78 kilometers seconds, because gravity is slightly stronger there and the circular orbit requires more centripetal acceleration. The revelation that orbital motion is fundamentally about speed rather than altitude transforms the understanding of every aspect of space travel. Getting to orbit is not about climbing, it is about accelerating. Staying in orbit is not about hovering, it is about falling in a specific way. The astronaut who feels weightless is not weightless because they have escaped gravity. They are weightless because they are in free fall, and everything in free fall near them is falling at the same rate. So there are no contact forces between them and their spacecraft. It is still present at full force, roughly 88% of its surface value for the ISS. The weightlessness is the feeling of falling. The relationship between orbital altitude and orbital velocity produces an important counterintuitive fact. Higher orbits are slower. The ISS at 400 kilometers moves at 7.66 kilometers seconds. The satellite at geosynchronous kilometers moves at 3.07 kilometers sections. The moon at 385,000 kilometers moves at approximately 1.2 kilometers sections. As distance from Earth increases, the orbital velocity decreases. This is the same relationship that makes outer planets orbit more slowly than inner planets in the solar system. Pluto's orbital velocity is only about 4.7 kilometers seconds, while Mercury moves at about 47.4 kilometers seconds. This relationship seems paradoxical to intuitions about going up and going faster. Shouldn't moving to a higher orbit require going faster? The answer is nuanced. Getting to a higher orbit does require going faster at some point in the maneuver. You fire your engines to raise the orbit. But once in the higher orbit, you are moving more slowly than you were in the lower orbit. The energy is stored in potential energy rather than kinetic energy. An analogy with mountain climbing helps. You expend energy climbing a mountain, but once at the top you are moving slower or not at all, with the energy now stored as gravitational potential energy rather than kinetic energy. Is a specific sense in which saying the International Space Station is above Earth is misleading in ways that matter for understanding spaceflight. The ISS is 400 kilometers from Earth's surface. In the conventional sense, that puts it above Earth in the same way a point 400 kilometers up a vertical line from the surface is above the surface. The orbital mechanics of the station make this framing functionally useless. Consider what would happen if you tried to think of the ISS as simply a location above Earth and tried to navigate to it by going up. You would need to accelerate upward with enough thrust to counteract gravity for the entire 400-kilometer climb. That requires substantial energy and propellant. Having arrived at 400 kilometers altitude with no horizontal velocity, you would be at the right altitude but completely unable to remain there. The station, moving at 7.66 kilometers seconds in its orbit, would have already moved approximately 2,760 kilometers from your position in the time it took you to climb straight up, even assuming you could do it in 6 minutes, which is physically impossible. You would then fall straight back down. The spatial relationship between the ISS and Earth is better understood dynamically. The station is in a relationship with Earth's gravitational field that maintains it at roughly constant distance from Earth's center. But this relationship requires continuous motion. The station's position relative to the ground changes by approximately 480 kilometers every minute along the orbital track. In one orbit, 90 minutes, it passes over approximately 40,000 kilometers of Earth's surface, covering a swath that shifts westward by about 2,200 kilometers from one pass to the next because Earth rotates beneath it. The approach to the ISS from the ground, a mission like a crewed Dragon or Soyuz launch, illustrates this perfectly. The rocket does not launch from Kennedy Space Center and fly directly to where the ISS is. It launches into an orbit whose altitude and inclination broadly match the ISS's orbit, and then over several hours, performs a series of engine burns that gradually adjust its orbit to rendezvous with the station's precise position at a specific future time. The navigation is entirely in the language of orbital mechanics, adjusting velocity vectors to achieve a specific orbit, not in the language of geometric direction, which is pointing the vehicle at the station and flying toward it. This is why docking is so counterintuitive. To speed up in an orbit, you fire your engine prograde in the direction of travel, which raises the far side of your orbit and actually causes you to end up moving more slowly relative to any station ahead of you. To close a gap between your spacecraft and a station slightly ahead of you in the same orbit, you must first slow down, dropping to a lower, faster orbit, catching up, and then raising your orbit back up to the station's altitude. The geometry is exactly backwards from intuitive driving experience, where to close a gap, you press the accelerator. The practical consequence of the ISS's orbital nature for mission planning is that launches to the station must be timed to take place within specific launch windows, narrow time intervals when the launch site's rotation has brought it to the correct position relative to the station's orbital plane. For launches from Kennedy Space Center to the ISS, the launch window is often only minutes wide, and if the rocket cannot launch within that window, it must wait until Earth's rotation brings the launch site back into alignment with the orbital plane, which happens approximately every 24 hours. Missing a launch window does not simply mean being late to an appointment. It means that the orbital planes do not align, and reaching the ISS from a misaligned orbit requires large plane change maneuvers that are extremely propellant intensive, sometimes more expensive in delta V than the original orbital insertion. The entire concept of being too late to catch a location that is defined by geometric position and distance, not by velocity and timing, makes no sense in orbital mechanics. The ISS is never in a fixed location relative to the launch site. The relationship between them is continuously evolving, and what matters is the alignment of orbital planes and the relative position within those planes, not vertical distance. The most productive way to understand orbital motion is to take Newton's thought experiment seriously. Newton imagined, in his Principia Mathematica, what would happen if you fired a cannonball from the top of a very high mountain with increasing horizontal velocities. At low velocities, it would follow a parabolic path and hit the ground some distance away. Higher velocities, it would travel farther before hitting the ground. At a specific velocity, the path would curve downward at exactly the rate that Earth's surface curves away, and the cannonball would travel all the way around the world and strike you in the back of the head. At even higher velocities, the path would not close on itself, and the cannonball would escape to infinity. This thought experiment makes the essential point. Orbit is not a state of being above the atmosphere or above gravity. It is a state of motion in which continuous free fall around a spherical body keeps the falling object at a constant distance from the body's center. The object is always falling. It never arrives at the bottom because the bottom keeps moving away. The free fall character of orbit explains weightlessness immediately. When you are in free fall, the only force acting on you is gravity, and because gravity accelerates everything equally regardless of mass, everything near you in the same free fall environment accelerates at the same rate. There are no contact forces between you and any surface because neither you nor any surface you might touch is accelerating differently from the other. You float not because gravity is absent, but because you and everything around you are falling together, synchronized by the same gravitational field. This is a crucial distinction that has practical implications for human health. Astronauts in free fall on the ISS are not out of gravity's reach, are in a gravitational field only marginally weaker than at the surface. The bone loss and muscle atrophy they experience are direct consequences of the absence of compressive loading, not of reduced gravity. On Earth, your bones and muscles are continuously stressed by supporting your weight against the gravitational pull. In free fall, that support load is gone, even though gravity is present. The body interprets the absence of compressive loading as the absence of need for structural support and begins to reduce bone density and muscle mass accordingly. Gravity is everywhere in the ISS environment. Fluid in a container fills it uniformly and clings to surfaces due to surface tension, not gravity. Dropped objects do not fall relative to their surroundings because everything is falling at the same rate. Gravitational gradient, the tiny difference in gravitational acceleration between the near side and the far side of the station, is technically measurable and creates extremely small tidal forces. These are negligible for most practical purposes. The point is not that gravity is absent. The point is that free fall eliminates the mechanical consequences of gravity for anything enclosed within the falling system. Implication that gravity is still fully present on the ISS has a subtle but important consequence for scientific experiments conducted there. Many experiments are sent to the station precisely to take advantage of what is called the microgravity environment, conditions in which the dominant effective gravity experienced by objects within the station is essentially zero because everything is in free fall together. This environment allows the study of physical and biological processes that are dominated by gravity on the ground, such as fluid dynamics in the absence of convection, crystal growth without sedimentation, and material processing without buoyancy-driven flows. But microgravity is not zero gravity. The residual accelerations experienced by objects on the station include tidal forces from the slightly different gravitational acceleration at different points within the station's volume, the extremely small atmospheric drag on the station that requires periodic reboosts, vibrations from crew activity and equipment operation, and tiny thermal effects. Combined residual acceleration environment on the ISS is not exactly zero, but ranges from roughly 10 to the minus 4 to 10 to the minus 6 G, depending on location and time. Scientific experiments that require even quieter environments must be placed at specific locations within the station or must be mounted on vibration isolation platforms. Tsiolkovsky rocket equation, derived in 1903, is the foundational constraint of all rocket propulsion. It expresses the relationship between the velocity change a rocket can achieve, its exhaust velocity, and the ratio of its initial mass to its final mass. Because propellant is consumed during the burn, every increment of velocity requires an exponentially larger fraction of the vehicle's initial mass to be propellant. This exponential relationship, the rocket equation's key feature, makes the goal of high velocity extremely expensive in mass and therefore in cost. The practical consequence for an orbital launch is sobering. A typical chemical rocket launching to low Earth orbit might have a mass fraction of roughly 85 to 90% propellant. Of the vehicle sitting on the launch pad, only 10 to 15% of the total mass will survive to reach orbit. The rest is propellant that is burned and discarded, along with the structural mass of tanks and engines that are shed in staging events. For a rocket carrying a 10-ton payload to orbit, the vehicle on the pad might weigh 200 to 500 tons. What makes this rocket equation reality relevant to the up versus sideways distinction is that almost all of this propellant mass is going toward building horizontal velocity. If the objective were simply to reach 400 kilometers altitude, the propellant requirement would be dramatically smaller. Gravitational potential energy difference between Earth's surface and 400 kilometers altitude corresponds to a velocity change of approximately 1.4 kilometers per second in an idealized direct ascent. The orbital velocity at 400 kilometers is 7.66 kilometers. The difference, plus losses from atmospheric drag and gravity drag during the ascent, means the effective velocity change required for a real orbital launch plus 9 to 10 kilometer seconds. Going to the right altitude represents roughly 15% of that. The other 85% is entirely about achieving the sideways velocity. This is why orbital launch is so expensive and why simple high-altitude flight, while impressive, does not approach the engineering challenge of orbital insertion. An aircraft flying at 30 kilometers altitude uses sophisticated engineering and substantial fuel to stay aloft, but it is doing something fundamentally different from reaching orbit. It is continuously generating lift to stay up. A spacecraft reaching orbit stops needing lift entirely. Once at orbital velocity, it has no need to continue thrusting to maintain altitude, and no aerodynamic surface is required. It simply falls in the right direction indefinitely. The staging approach used in multi-stage rockets is one of the primary strategies for managing the rocket equation's demands. A single-stage rocket that needs to deliver the full orbital delta-v must carry all of its propellant from the ground, meaning the early burns must accelerate not only the payload and the structure required to enclose it, but also all the propellant that will be used later in the mission. By staging, vehicle discards the now empty tanks and engines that are no longer needed, reducing the mass that subsequent stages must accelerate. This dramatically improves the achievable mass fraction for the payload. The Saturn V, which remains the most powerful rocket ever to reach orbit, and which sent humans to the moon, was a three-stage vehicle. The first stage burned for approximately 2.5 minutes, consuming roughly 2,000 tons of propellant and delivering approximately 2.7 kilometers seconds of velocity. The second stage burned for 6 minutes, consuming roughly 450 tons of propellant and adding approximately 4.4 kilometers seconds. The third stage performed 2 burns, first to complete orbital insertion and second to perform the translunar injection burn. The initial vehicle on the pad weighed approximately 2,970 tons, of which roughly 96% was propellant and structural mass that would be discarded before reaching the moon. The cost of this propellant mass, the manufacturing and operational costs of the vehicles that carry it, is the fundamental driver of launch costs. Reducing costs requires either more efficient propellants, more efficient engines, reusable structures, or some combination. The current era of commercial spaceflight has focused primarily on reusability, recovering and refurbishing rocket components rather than discarding them after a single use. Gravity turn maneuver that every orbital rocket executes after clearing the launch tower is the physical expression of the up versus sideways insight in hardware. It reveals, through the vehicle's actual behavior, what the mission is actually trying to accomplish. Watching it in detail is one of the clearest possible illustrations of what getting to space actually means. A rocket standing on the launch pad is aligned vertically. Everything about the pad environment, the hold-down clamps, the access arms, the flame trench, is oriented for a vehicle pointed straight up. The first seconds of flight are vertical, building enough velocity and altitude to clear the infrastructure and to allow the vehicle to begin its pitch program. These vertical seconds are essentially overhead, necessary to clear the immediate environment but not directly contributing to the orbital insertion goal. As soon as the vehicle is clear, the attitude control system initiates the pitch over, tilting the nose of the vehicle in the direction of the target orbit's inclination. The rocket continues to fire, but now the thrust vector, the direction the engine is pushing the vehicle, is increasingly horizontal. Gravity is pulling the vehicle downward at approximately 9.8 meters per second squared. The engines are providing a thrust acceleration that is being directed mostly sideways. The result is that the vehicle follows a curved path, climbing in altitude while accelerating rapidly in the horizontal direction. The trajectory shape is not arbitrary. It is optimized, within the constraints of aerodynamic loading and structural limits to minimize the total propellant consumption for the mission. Different trajectories from the same starting point to the same orbital insertion point use different amounts of propellant, and the actual trajectory chosen by the launch team's trajectory planning software is the one that minimizes this consumption while meeting all constraints. The term gravity turn comes from the fact that gravity itself does much of the work of turning the trajectory. Once the vehicle begins pitching over and the angle of attack is kept near zero, only forces acting are gravity pulling downward and thrust pushing roughly along the velocity vector. Gravity, acting perpendicular to the velocity, continuously curves the path. The name captures the physical reality. Gravity is doing the turning. The vehicle is not fighting gravity to go up. It is using gravity as part of the turning mechanism that converts vertical velocity into horizontal velocity. The heating environment during the lower atmosphere phase of ascent also plays an important role in the design of the pitch-over maneuver. As the rocket accelerates through the dense lower atmosphere, dynamic pressure on the vehicle, proportional to the atmospheric density times the square of the velocity, rises to a maximum at the point of maximum aerodynamic loading called max Q. This typically occurs between 10 and 15 kilometers altitude, where the atmosphere is still relatively dense and the vehicle is moving at supersonic speeds. Structural engineers design the vehicle to withstand the aerodynamic forces at max Q, and the control systems must manage the trajectory to keep aerodynamic loads within structural limits at this point. After max Q, as the vehicle climbs higher and the atmosphere thins, the aerodynamic loads decrease rapidly. The vehicle can then adopt more aggressive pitch angles without risk of aerodynamic failure. Transition from the relatively restrained pitch over of the lower atmosphere to the more rapid horizontal acceleration of the upper atmosphere and near vacuum is visible in the trajectory as a change in the rate at which the vehicle's attitude changes. By the time the vehicle is above roughly 80 kilometers, aerodynamic forces are negligible and the trajectory is determined entirely by the balance of gravitational and thrust forces. The entire profile from liftoff to orbital insertion typically takes between 8 and 12 minutes for most orbital launch vehicles, with the first minute or two devoted to the vertical ascent and the remaining 6 to 10 minutes devoted to the horizontal acceleration phase. In those 10 minutes, the vehicle goes from zero velocity on the launch pad to orbital velocity in approximately circular orbit. The statement that there is no up in space deserves more precise treatment than it typically receives. It is true, but requires qualification to be fully accurate. The precise statement is that there is no preferred up direction that applies universally throughout space. Any local region near a massive body has a well-defined local up direction defined by the gradient of the gravitational potential. Near Earth, Up means away from Earth's center. Near the moon, up means away from the moon's center. In the middle of interplanetary space, far from any large mass, the gravitational field is so weak and so nearly uniform that no meaningful up direction exists at all. Consider the experience of traveling from Earth to Mars. During launch from Earth is well defined, away from Earth's surface. During the months-long transit between planets, in the vast emptiness of interplanetary space, there is no physical basis for an up direction. The spacecraft and its occupants are in free fall along a solar orbit that will intersect Mars's orbit at the time of arrival. There is a gravitational acceleration toward the Sun throughout the journey. It is extremely weak and essentially uniform throughout the spacecraft, producing no sensation for the occupants and no preferred orientation for the vehicle. The spacecraft can point in any direction. The crew can arrange their sleeping positions in any orientation relative to the vehicle's body, and no physical sensation will distinguish one arrangement from another. Absence of up in interplanetary space creates practical challenges for human psychology and habitat design that are quite different from those in low Earth orbit. On the ISS, while the crew is technically weightless, they maintain a consistent orientation convention. Decks and ceilings are clearly marked. The modules are arranged so that visiting crew members can navigate intuitively. This convention is artificial but comfortable, providing a psychological substitute for the gravitational up that actually exists just outside the vehicle. For a long interplanetary voyage, convention becomes simultaneously more important and potentially more arbitrary. With no gravitational field providing even a theoretical up reference, the choice of orientation is entirely conventional. Designers of future Mars transit vehicles face the interesting problem of whether to provide artificial gravity through rotation, which provides a real up direction but requires large rotating structures, or to accept the weightless environment, which is cheaper and mechanically simpler, but imposes the known physiological penalties of long-duration microgravity. Convention of referring to high orbits as higher than low orbits, or to the moon as above Earth, is linguistically convenient and not wrong in a limited technical sense. Geosynchronous orbit does have greater potential energy than low Earth orbit, and the moon is farther from Earth's center than the ISS. This technical sense of higher obscures the fact that nothing is up in the way that language implies. A satellite in geosynchronous orbit is not above Earth in any experiential or motivational sense. At a specific orbital radius, with a specific orbital energy, the word above contributes nothing to understanding its situation that orbital radius and orbital velocity do not already convey more precisely. The language of deep space amplifies the problems. When we say a probe is in deep space, the word deep suggests an abyss, a void below, something one falls into. But the interplanetary medium is not below anything. It is the domain between gravitational wells, the spaces where no single massive body dominates the local gravitational field. Voyager 1, currently in the interstellar medium beyond the heliosphere, is not below or above anything. It is moving outward from the solar system at roughly 17 kilometers/seconds in a direction roughly toward the constellation Ophiuchus, in a region of space where the sun's gravitational influence is still weakly felt, but where no local massive body defines a meaningful up direction. Vestibular system, located in the inner ear, is the primary sensory organ responsible for the human sense of up and down and for equilibrium and balance. It consists of two main components: the semicircular canals, which detect rotational accelerations, and the otolith organs, specifically the utricle and saccule, which detect linear accelerations, including the constant linear acceleration of gravity. The otolith organs contain tiny calcium carbonate crystals called otoconia that rest on a gelatinous membrane. When the head tilts or when linear acceleration occurs, the otoconia deflect the membrane, stimulating hair cells that send neural signals to the brain. The brain interprets the signals from the otolith organs as indicating both the direction of gravity and any linear acceleration. This works beautifully on Earth because the dominant signal in the otolith organs is always the constant gravitational acceleration of 9.8 meters per second squared, which provides an unambiguous reference direction. Up is the direction opposite to this signal. In the microgravity environment of orbit, the otolith organs receive no gravitational signal at all because the occupant is in free fall. The otoconia do not deflect the membrane because there is no net force between the person and their surroundings. The vestibular system, deprived of its primary reference, can no longer determine which way is up from gravitational signals alone. It falls back on visual information, the pattern of what is floor and what is ceiling in the habitat, and on other proprioceptive cues. These are no longer anchored to any physical reality beyond human convention. The result is the well-documented phenomenon of space motion sickness, formerly called space adaptation syndrome, which affects roughly 70% of astronauts in the first days of a mission. The condition is caused by the conflict between different sensory systems. The visual system may report information consistent with a particular orientation, while the vestibular system is sending ambiguous or unusual signals, and the proprioceptive system from joints and muscles reports pressure patterns inconsistent with Earth normal posture. The brain, trying to reconcile these conflicting inputs, often experiences nausea, disorientation, and malaise. The symptoms typically resolve within 2 to 3 days as the brain recalibrates to the new environment. The up feeling, which seems as absolute and certain as any sensation a person can have, is revealed by orbital experience to be a constructed inference. The brain takes the signal from the otolith organs, combines it with visual and proprioceptive information, applies a lifetime of prior expectation, and presents to consciousness the experience of knowing which way is up. Remove the gravitational signal, and the construction process is disrupted. What remains is the brain's best guess based on incomplete information, which in a novel environment like orbit is frequently wrong. The brain's construction of the up sensation is also influenced by head position relative to the body. When you tilt your head to the side, the otolith organs signal that the gravitational direction has changed relative to your head. The brain interprets this correctly as head tilt rather than a change in the direction of gravity. The interpretation requires a model that has been built through experience. Infants take months to develop accurate upright orientation, and the neural circuits that underlie this interpretation are learned, innate. In microgravity, astronauts sometimes experience a specific illusion called the inversion illusion, in which the visual scene appears to flip upside down. This occurs because the brain's model of orientation, derived from a lifetime of gravitational experience, does not match the absence of gravitational input. The visual system's interpretation of the scene is distorted by the failed model. The feeling of being upside down in orbit is not unusual in the first days of a mission, particularly when moving through large spaces or when looking at Earth through the window in an unexpected body orientation. Adaptation that eventually resolves space adaptation syndrome involves the brain learning to give less weight to the vestibular signals that conflict with the visual information, and to rely more heavily on vision and internal body models for orientation. This recalibration is sufficiently reliable that most astronauts return from long missions without the severe disorientation that the first days might suggest, though the reverse adaptation on return to Earth, readapting to the presence of gravity, creates a different set of challenges. Astronauts who have described their experience of first entering the microgravity environment of the ISS after several days' transit in the relatively compact Soyuz or Dragon spacecraft consistently report something that is difficult to describe to ground-bound audiences. Disorienting experience of entering a large space in which every direction is equally valid. The ISS modules can be entered from any hatch. A crew member floating from one module to another can arrive in an orientation that is inverted relative to the modules labeled floor and ceiling. First weeks of a mission involve learning to see this orientation as completely normal and to navigate freely in three-dimensional space without the constant subconscious anchor of a gravitational down. Some astronauts report that after extended time in orbit, the Earth itself begins to seem like an optional reference rather than an absolute one. Looking out the window at the planet below produces what some describe as a new visual experience. The Earth is simply the largest visible nearby object, curved and luminous, below nor above in any felt sense, simply in a particular direction relative to the current window orientation. Intellectual knowledge that they are falling toward it at great speed is not accompanied by any sensation of falling, and the visual impression of the enormous planet out the window competes for psychological dominance with the interior visual cues from the habitats marked floors and ceilings. Engineering of spacecraft interiors addresses this challenge in consistent ways. The International Space Station's modules have labeled floor and ceiling, color-coded in some cases, and are arranged so that their internal conventions are mutually consistent. Moving from one module to another along the main axis, you can maintain the same orientation and the same up direction. Japanese experiment module is oriented so that its floor and ceiling align with those of the US segment it connects to. This consistency is maintained deliberately because inconsistent orientation conventions across modules would create significant navigational difficulty for crew members already adapting to weightlessness. Future long-duration space habitats and transit vehicles will need to make deliberate decisions about these orientation conventions in the absence of any physical anchor. The choice will partly depend on the mission profile. A vehicle rotating to provide artificial gravity has a natural up and down defined by the centrifugal acceleration. A non-rotating vehicle does not, and the habitat designers must choose an arbitrary convention and apply it consistently enough that it becomes habitual for the crew. Documentation of spatial disorientation in microgravity extends back to the early human spaceflights of the 1960s. Yuri Gagarin, during his 108-minute orbital mission in 1961, reported a visual world that seemed perfectly normal during the brief periods he spent near the window, suggesting that visual orientation cues dominate quickly in the absence of vestibular signals. Later missions with longer durations and larger habitable volumes provided more detailed accounts of the adaptation process. The phenomenon of being spatially lost inside the ISS, of moving through a hatchway into a module from an unexpected direction and temporarily being unable to identify which direction is the labeled floor, is reported by virtually every new crew member. Experienced crew members learn to navigate by the distinctive visual features of each module, by the locations of specific equipment racks, by the colors of cables and connectors, by the orientations of labels and screens. These learned navigation cues substitute for the gravitational orientation that is absent. The navigation becomes automatic and confident with experience, yet it is a learned skill rather than an extension of Earth-based orientation intuition. One consistently reported experience is the comfort of seeing Earth out the window. The planet provides a reliable external visual reference, one that is unambiguous about its own orientation even if astronauts cannot orient themselves within the module. Earth is the blue and white sphere that dominates the view from the window, and regardless of the astronaut's body orientation within the spacecraft, the planet is identifiable, unmistakable, psychologically grounding in the literal sense. Apollo missions are the most audacious human spaceflight achievement in history. The trajectory that put humans on the moon is one of the most intricate pieces of orbital mechanics engineering ever executed in practice. Understanding what Apollo actually did, rather than the simplified version that the phrase "going to the moon" suggests, reveals how thoroughly the up intuition fails even for the journey to Earth's closest natural neighbor. The Saturn V rocket launched from Kennedy Space Center and performed a standard orbital insertion, following the pattern described earlier. A vertical ascent to clear the launch tower, a gravity turn to build horizontal velocity, main engine cutoff at target altitude, and arrival in a parking orbit around Earth at approximately 185 kilometers altitude. At this point, crew and their spacecraft were not yet going to the moon. They were in Earth orbit, traveling at approximately 7.8 kilometers per second sideways, waiting. Key maneuver that actually sent them to the moon was the translunar injection burn performed by the SIVB third stage engine while the spacecraft was over a specific point in its orbit, such that the resulting trajectory would intercept the moon 3 days later. The burn increased the spacecraft's velocity from roughly 7.8 kilometers seconds to roughly 10.8 kilometers seconds, enough to escape Earth's gravitational well and follow an elliptical trajectory whose apex was in the vicinity of the moon. The burn was performed in the horizontal direction, not toward the moon. The spacecraft did not point at the moon and fire its engines. It pointed in the direction of its orbital velocity and fired its engines, raising its orbit until the far end of the ellipse reached the moon's vicinity. After the burn, the crew was in what is called a free return trajectory, meaning that if no further engine burns were performed, the spacecraft would swing around the moon and return to Earth without any additional propulsion. This was a safety feature designed into the mission profile after the Apollo 1 fire. The spacecraft traveled toward the moon for 3 days, decelerating as it climbed out of Earth's gravitational well, then accelerating as it fell into the moon's gravity, no point pointing directly at the moon or traveling directly toward it in the geometric sense. Arriving at the moon required a lunar orbit insertion burn that slowed the spacecraft enough to be captured by the moon's gravity into a lunar orbit. The burn was a deceleration. The engines were fired backwards, relative to the direction of travel, reducing velocity. The spacecraft did not arrive at the moon by going toward it. It arrived by slowing down relative to the moon at the right moment to be captured. The lunar module's descent to the lunar surface adds another layer to the non-up story. LM did not simply descend vertically onto the moon from lunar orbit. The powered descent began while the LM was in a low lunar orbit, moving horizontally at roughly 1.6 kilometers sescons. The descent engine fired to reduce this horizontal velocity while also managing the vertical component of the trajectory, guiding the spacecraft along a complex, three-dimensional path that brought it to a near hover above the landing site. The final approach was nearly horizontal rather than vertical. The astronauts spent much of the powered descent looking not downward but forward and somewhat downward, using visual cues from the approaching terrain to monitor the trajectory. Ascent from the moon was similarly non-vertical in its dominant velocity component. The ascent engine had to provide both the vertical velocity to lift off and the horizontal velocity to reach lunar orbital speed, approximately 1.6 kilometers seconds. Like an orbital launch from Earth but in miniature, the ascent from the moon was primarily about building horizontal velocity rather than climbing vertically. The ascent stage, after lifting off, followed a curving trajectory that matched it to the command module's orbit in what was one of the most complex and highest-stakes rendezvous maneuvers in spaceflight history, all performed by astronauts using a guidance computer with roughly the computing power of a modern digital wristwatch. The Van Allen radiation belts are two donut-shaped regions of charged particles trapped by Earth's magnetic field and centered roughly on the magnetic equator. The inner belt extends from approximately 1.0 to 6,000 kilometers above Earth's surface. The outer belt extends from approximately 13,000 to 60,000 kilometers. Between and around these belts are regions of more moderate radiation. The belts themselves represent radiation environments that are genuinely dangerous to unprotected biological tissue and to sensitive electronic equipment. The radiation in the Van Allen belts consists primarily of high-energy protons and electrons trapped by the magnetic field lines, spiraling back and forth between the magnetic poles. The inner belt contains predominantly high-energy protons, some at energies exceeding 100 million electron volts, capable of penetrating significant thicknesses of aluminum shielding. Outer belt contains predominantly high-energy electrons in the million electron volt range. The ISS orbits at 400 kilometers altitude below the inner Van Allen belt and with the benefit of Earth's magnetic field providing significant shielding against galactic cosmic rays. Astronauts on the ISS receive radiation doses that are elevated above Earth's surface levels, but are within manageable ranges for missions of 6 months to a year. The long-term health effects of these doses are a significant concern for human spaceflight, but not immediately life-threatening. Going beyond low Earth orbit, going up in the sense that takes you through the Van Allen belts, exposes travelers to dramatically higher radiation doses. The Apollo missions to the Moon passed through the belts of the universe, and this remains one of the most technically remarkable aspects of those missions. The crews were in the belts for a sufficiently short time, and the mission timing was chosen to avoid periods of enhanced solar activity, that the doses received were within acceptable limits for the mission duration. Those limits were carefully calculated, and margins were not large. For future missions that would take crews to higher Earth orbits, to the Moon with longer surface stays, or to Mars, the Van Allen belts represent a real design driver that shapes both the trajectory and the shielding requirements of any spacecraft passing through them. The inner belt's high-energy proton population is primarily produced by the decay of neutrons generated when cosmic rays interact with Earth's upper atmosphere. These neutrons, some of which would otherwise escape into space, are moving in directions that bring them into the Earth's magnetic field, where they decay into protons and electrons. The protons are then trapped by the magnetic field lines, bouncing between the magnetic poles with periods of seconds, drifting longitudinally around Earth over periods of minutes to hours, and potentially remaining trapped for years before diffusing into the atmosphere. The outer belt's electron population is more dynamic. Outer belt responds rapidly to geomagnetic storms driven by solar coronal mass ejections. During a strong storm, the outer belt can expand in both altitude extent and particle flux by factors of 10 or more within hours. Satellites in geosynchronous orbit routinely experience anomalous events during geomagnetic storms, with spacecraft electronics showing increased error rates and occasional permanent failures due to electrostatic discharge from the enhanced electron population. Outer belt's variability makes it a more challenging environment to design hardware for than the inner belt, whose population is more stable. The Parker Solar Probe's trajectory, which takes it closer to the Sun than any previous spacecraft, passes through the inner Van Allen belt each time it uses Earth for a gravity assist. spending only a short time in the highest radiation regions. The probe's electronics are shielded primarily by a carbon composite heat shield, but also by the relatively short transit time through the worst radiation zones. Escape velocity is one of the most commonly misunderstood concepts in popular discussions of space, and the misunderstanding usually takes the form of imagining it as the speed needed to fly straight up fast enough that gravity cannot pull you back down. This picture is wrong in ways that matter. Escape velocity from Earth's surface is approximately 11.2 kilometers per second. The common presentation of this is, if you fire a projectile straight up at this speed, it will never fall back to Earth. This is technically correct, but profoundly misleading about what escape velocity actually means in the context of spacecraft. No spacecraft attempting to leave Earth actually fires straight up at 11.2 kilometers seconds. Correct understanding of escape velocity is that it is the minimum speed needed at a given distance from a massive body to reach infinite distance without any additional propulsion. It does not specify the direction. A spacecraft moving at 11.2 kilometers seconds at Earth's surface in any direction, not just straight up, is moving at escape velocity. If it is moving horizontally at that speed and is above the atmosphere so that it does not hit the ground due to Earth's curvature, it will escape to infinity. The direction does not matter, only the speed. In practice, spacecraft leaving Earth orbit for other destinations do not accelerate to escape velocity at once. Instead, they use the Oberth effect. They burn their engines at the lowest point of their orbit, where their velocity is already high, because performing a burn at high velocity produces more change in orbital energy per unit of propellant than the same burn at low velocity. A spacecraft in low Earth orbit at 7.66 kilometers needs to add only about 3.2 kilometers seconds to reach escape velocity. This is far more efficient than launching to escape velocity from the ground, because the propellant needed to achieve those last 3.2 kilometers seconds is being carried to orbital altitude by the launch vehicle, paid for once, and then used efficiently in vacuum with no atmospheric drag. The notion of escape velocity as going up fast enough frames the problem in terms of altitude, as if the issue is that the gravity weakens with height until at some distance it can no longer hold you. While it is true that gravitational acceleration decreases with distance, escape velocity is better understood as a statement about total mechanical energy. A spacecraft with kinetic energy exceeding the gravitational potential energy has positive total mechanical energy and will not return. This is an energy statement, not an altitude statement. The Oberth effect, named after the German physicist Hermann Oberth, who described it in the 1920s, explains why performing engine burns at low altitude in orbit is more efficient than performing them at high altitude. When a spacecraft is moving fast, a given change in velocity produces a larger change in kinetic energy than when the spacecraft is moving slowly, because kinetic energy scales with velocity squared. A burn that adds 1 kilometer per second to a spacecraft moving at 8 kilometers per second adds more kinetic energy than the same burn adds to a spacecraft moving at 1 kilometer per second. Means that the most efficient place to perform an escape burn, or any burn that aims to dramatically increase orbital energy, is at the lowest possible point of the existing orbit where orbital velocity is highest. The Space Shuttle, for example, would have been most efficiently deployed to a geosynchronous orbit by launching to low Earth orbit first, and then performing the geosynchronous transfer burn from the lowest point of the transfer orbit. The same logic applies to interplanetary missions. The translunar injection burn for Apollo was performed in low Earth orbit, where the spacecraft was already moving at 7.8 kilometers seconds, rather than at a higher orbit where the velocity would have been lower, and the same delta V would have produced less energy increase. This elegant piece of orbital mechanics is one of the most concrete examples of how the up intuition fails in spaceflight. Counterintuitively, you want to be as low as possible when you fire your engines to go as far as possible. The energy you gain from the burn is maximized by the high velocity you already have from being in a tight orbit rather than a slow, high orbit. The word space, when used to mean the region beyond Earth's atmosphere, encompasses an enormous range of very different environments, none of which is simply up from the surface in any single directional sense. Understanding the different orbital regimes above Earth illustrates how multiple, distinct physical environments are stacked in the radial direction from Earth's center, each with its own character, uses, and challenges. Low Earth orbit, typically defined as altitudes from 200 to 2,000 kilometers, is where the ISS operates and where most human spaceflight has taken place. At these altitudes, the orbital periods range from roughly 88 minutes at the lowest sustainable altitude to roughly 127 minutes at 2,000 kilometers. The atmosphere is thin but not completely absent, and spacecraft in LEO experience very slight drag from the residual atmosphere that causes their orbits to decay slowly over time, requiring periodic reboosts to maintain altitude. Medium Earth orbit, from 2,000 to approximately 35,786 kilometers, contains the GPS satellite constellations and other navigation systems, which operate at approximately 20,200 kilometers. The region from roughly 13,000 to 60,000 kilometers is dominated by the outer Van Allen radiation belt, making it inhospitable for both human occupants and electronic systems without heavy shielding. Geosynchronous orbit at 35,786 kilometers is a remarkable and extremely useful special case. At this altitude, the orbital period is exactly 24 hours, matching Earth's rotation rate. A satellite in a circular geosynchronous orbit over the equator, called a geostationary orbit, remains stationary relative to the ground, appearing to hover over a fixed point. Communications satellites, weather satellites, and many others occupy this ring around Earth. Reaching geosynchronous orbit requires considerably more energy than reaching low Earth orbit, approximately twice as much delta V in total, making it a more expensive destination. Beyond geosynchronous orbit, the Moon orbits at approximately 385,000 kilometers. Earth-Moon system's Lagrange points are at various distances up to about 1.5 million kilometers from Earth, and the Sun's gravitational influence increasingly dominates over Earth's at distances beyond roughly 1 million kilometers. The transition from Earth-dominated to Sun-dominated space is called the sphere of influence, and trajectories through this region must account for both gravitational sources. The Lagrange points of the Earth-Moon system represent another class of special orbit, locations where the gravitational forces from Earth and the Moon combine with the centrifugal force in the rotating reference frame to produce equilibrium points. The 5 Lagrange points, labeled L1 through L5, are locations where a small object can maintain a fixed position relative to both Earth and the Moon with minimal station keeping. L1, between Earth and Moon at approximately 60,000 kilometers from the Moon, and L2, directly behind the Moon at roughly the same distance, are of interest for lunar relay communications and future lunar gateway stations. The James Webb Space Telescope is located at the Sun-Earth L2 point, approximately 1.5 million kilometers from Earth, in the direction away from the Sun. At this location, orbits the Sun in a halo orbit around L2, maintaining a fixed position relative to both Earth and the Sun, while Earth shields it from solar radiation on one side and the deep cold of space allows its detectors to cool on the other. The choice of L2 for Webb was not about going up in any conventional sense. It was about finding the orbital configuration that provided the thermal environment and communication geometry that the telescope's science objectives required. Every orbital location in this hierarchy, from the ISS at 400 kilometers to Webb at 1.5 million kilometers to the Moon at 385,000 kilometers, represents a specific set of trade-offs between orbital energy, transit time from Earth, radiation environment, communication delay, and mission objectives. The vocabulary of up and above is too one-dimensional to capture any of these distinctions. If getting to orbit is primarily about gaining sideways velocity rather than altitude, then leaving orbit is primarily about losing that sideways velocity. The problem of re-entry is not the problem of coming down from a high place. It is the problem of dissipating an enormous amount of kinetic energy, the energy of traveling at 7.66 kilometers seconds before the vehicle reaches the ground. A spacecraft in low Earth orbit has kinetic energy of approximately 29 million joules per kilogram of mass. A spacecraft returning from the Moon has even more, arriving at Earth's vicinity at roughly 11 kilometers seconds. This energy must be converted into something else before landing. The options available to spacecraft designers are limited. Energy can be dissipated as heat through aerodynamic braking in the atmosphere. It can be converted into potential energy by transferring it to another object through propulsive braking, or it can be rejected through some combination of these. All human spacecraft to date have used aerodynamic braking. They dive into Earth's atmosphere at orbital velocity, and the friction between the spacecraft's heat shield and the increasingly dense air converts the kinetic energy to heat. The heat is managed by ablative heat shields that absorb energy by melting, vaporizing, and radiating, or by reinforced carbon-carbon ceramic tiles like those on the space shuttle that resist the temperature without ablating. The temperatures involved are extraordinary. The leading edges of a spacecraft during atmospheric re-entry reach roughly 1,650 to 2,000 degrees Celsius for a standard low Earth orbit return, and up to 700 degrees Celsius or more for a return from the Moon. The crucial point for the up versus sideways distinction is that the spacecraft does not simply fall straight down during re-entry. It enters the atmosphere at a shallow angle, typically around 5 to 7 degrees below horizontal, and uses the atmosphere as a braking medium over hundreds of kilometers of horizontal distance. At the end of this atmospheric braking, the spacecraft has lost most of its orbital velocity and is effectively in a ballistic trajectory, or, for winged vehicles, in aerodynamic flight. The descent to the ground is then managed by parachutes, retrorockets, wings, or some combination. The ground impact is the final tiny fraction of a journey that was never primarily about going straight down any more than the launch was about going straight up. Space Shuttle's re-entry trajectory illustrated the sideways character of re-entry more vividly than most other vehicles, because the shuttle was a winged vehicle that generated aerodynamic lift during the descent. The shuttle performed a deorbit burn that reduced its orbital velocity by approximately 100 to 200 meters per second, a tiny fraction of its 7.66 kilometers second orbital velocity, to lower the far side of its orbit so that it would intersect the upper atmosphere. The burn was performed half an Earth orbit before the landing site, Z, typically over the Indian Ocean for landings at Kennedy Space Center in Florida. After the deorbit burn, the shuttle traveled half an orbit, approximately 20,000 kilometers, before reaching the atmosphere's significant density. Entry interface, the point at which aerodynamic forces became significant, occurred at roughly 120 kilometers altitude and approximately 8 zone kilometers from the runway. The vehicle then spent approximately 30 minutes in the atmosphere, decelerating from orbital velocity to landing speed over that 8,000-kilometer horizontal distance. Trajectory during atmospheric descent was not vertical. The shuttle performed a series of S-turns, banking to one side and then the other, to control the rate of energy dissipation and to steer toward the runway. The landing itself was the only truly downward phase of the entire mission. The final approach and touchdown at Kennedy Space Center. But even this was not straight down. The shuttle landed on a runway like a conventional aircraft, albeit an unpowered one, touching down at roughly 350 kilometers per hour. The entire re-entry from orbit to runway was a controlled conversion of horizontal velocity into heat and then into a conventional aircraft landing approach. It is worth asking what an actual straight-up journey to interplanetary space would look like and what it would cost. To concretize how different this is from orbital insertion, thought experiment illuminates the enormous energy cost of altitude alone and why no actual space mission ever works this way. Suppose you wanted to travel straight up from Earth's surface to the distance of the Moon, roughly 385,000 kilometers, moving only radially outward from Earth's center and arriving at that distance with zero velocity. Gravitational potential energy difference between Earth's surface and lunar distance is approximately 62 million joules per kilogram. Converting this to velocity equivalent using the rocket equation with a specific impulse typical of chemical propulsion. Achieving this straight-up journey with a minimal mass ratio would require roughly 1 kilometer seconds of delta V, slightly less than escape velocity. Having arrived at lunar distance with zero velocity, you would then be in the gravitational field of the Moon, Earth, and Sun simultaneously. You would need additional velocity to do anything useful, including entering lunar orbit, making a soft landing on the Moon, or traveling onward to Mars. You would also have arrived at a specific point in space at a specific time, and the Moon would likely not be there. The Moon is orbiting Earth continuously. Arriving at the Moon requires arriving at the right distance, at the right time when the Moon is present. This thought experiment illustrates why space navigation is fundamentally about trajectories through time rather than positions in space. Destination like the Moon is not a place you can point at and travel toward. It is a place that will be at a certain location at a certain future time. Exact trajectory of your spacecraft must be calculated to intercept that location at that time. The planning is four-dimensional, requiring knowledge of where every relevant body will be throughout the mission. Real missions to the Moon do not go straight up. They use the Hohmann transfer approach, inserting into an elliptical orbit that touches the Moon's orbital radius at its far end, with the burn calculated, so that the spacecraft arrives at that far end precisely when the Moon passes through it. This is far more energy efficient than a straight-up journey and automatically delivers the spacecraft with the right velocity to be captured into lunar orbit. Geometric upward path to the Moon is not a path anyone has ever followed or will ever follow. The energy accounting for interplanetary missions reveals the same fundamental principle at every scale. A mission to Mars does not simply travel from Earth's orbital position to Mars's orbital position. It follows a carefully planned arc within the solar gravitational field called a Hohmann transfer orbit, or a more complex trajectory optimized for specific constraints. Carries the spacecraft from Earth's orbit to Mars's orbit over a transit time of approximately 6 to 9 months, depending on the specific trajectory chosen and the positions of the planets. The launch from Earth for a Mars mission begins with insertion into Earth parking orbit at roughly 7.8 kilometers seconds. The trans-Mars injection burn then adds approximately 3.6 kilometers seconds at low Earth orbit, raising the far end of the transfer ellipse to the Martian distance of roughly 1.5 astronomical units from the Sun. For the entire transit, the spacecraft is in free fall along this ellipse, moving neither up nor down in any absolute sense, but along a curved path determined by the Sun's gravity and the initial conditions of the injection burn. Upon arriving at Mars, a spacecraft is moving at a velocity that is too fast for direct capture by Mars's gravity, and a capture burn or aerobraking maneuver must be performed to slow the spacecraft into Martian orbit. The entire architecture of the mission, the Earth orbit parking phase, the injection burn, the interplanetary transit, the Mars capture is described entirely in the language of orbital mechanics and velocity changes. The word up appears nowhere in the mathematical description of any part of it. The most expansive version of the orbit as falling insight is the recognition that every large-scale gravitational system in the universe operates by the same principle. Everything is always falling toward everything else, and the patterns we call orbits, galaxies, galaxy clusters, and the large-scale structure of the universe are all manifestations of matter falling in various configurations through the gravitational fields created by all the other matter. The moon is falling toward Earth. It is not held up by any force. There is no surface tension in space, no string connecting it to Earth, no mystical repulsion that counteracts gravity at lunar distance. The moon is in free fall toward Earth, and it is falling sideways, fast enough that it misses Earth and continues around. Earth is falling toward the Sun, which is why Earth orbits the Sun. The solar system as a whole is falling toward the center of the Milky Way, orbiting the galactic center at about 220 kilometers per second, with an orbital period of roughly 225 to 250 million years. The Milky Way is falling toward the Andromeda Galaxy in a trajectory that will bring the two galaxies into a merger event in approximately 4 to 5 billion years. The local group of galaxies, which contains both the Milky Way and Andromeda, is falling toward the Virgo cluster as part of the large-scale gravitational structure of the cosmic web. The cosmic web itself evolved from the primordial density fluctuations of the early universe through the process of gravitational collapse. Matter falling toward overdense regions, forming filaments and nodes, emptying the great voids. None of these systems are being held up by any force opposing gravity. All of them are in free fall toward the other massive objects that influence them. And the difference between a falling rock and an orbiting moon is purely one of velocity. The rock is not moving fast enough to miss Earth during its fall, while the moon is. The orbit, as continuous falling insight, applied at all scales, dissolves the intuition that things in stable orbits are somehow resisting gravity, are simply complying with it in a way that keeps them at approximately constant distance from their central attractor. Insight that gravity is universally attractive, and that stable configurations require orbital motion rather than static suspension, has a history in physics that parallels the development of celestial mechanics. Before Newton, the question of why the moon does not fall down was a genuine puzzle. Newton's genius was to recognize that the moon is falling. It is continuously accelerated toward Earth. The question is not why it does not fall, but why it falls in a closed curve. His calculation that the gravitational acceleration at the moon's distance, scaled from the surface value by the inverse square law, matched the centripetal acceleration required for the moon's observed orbital period, was the empirical confirmation of universal gravitation. The same logic, applied to the solar system, explains why planets orbit rather than falling into the sun or floating away. The solar system is approximately 4.5 billion years old, and every planet has been continuously falling toward the sun for that entire duration, continuously missing, because their sideways velocities are sufficient to carry them around rather than into. The orbits are not perfectly stable over geological timescales. Gravitational interactions between planets perturb each other's orbits very slightly, and on billion-year timescales, these perturbations accumulate in ways that slightly change the shapes of the orbits. But on human timescales, the solar system's orbital architecture is essentially permanent. The dark matter halos of galaxies play an analogous role on galactic scales, providing the gravitational well within which stars orbit rather than fly off into intergalactic space. Acceleration of the universe's expansion by dark energy introduces a complication at the largest scales. Galaxies and galaxy clusters that are sufficiently distant are being carried away from each other by the expansion faster than gravity can overcome. But within gravitationally bound systems, the same principle applies. Everything is falling, and everything stays at roughly constant distance from everything else because it is falling sideways, fast enough to keep missing. There is a particular cognitive shift that occurs when the orbital mechanics perspective truly settles in, when the picture of orbit as altitude gives way to the picture of orbit as velocity and free fall. It is something like learning to see a different aspect of the visual world, one that was always present but invisible until the right frame of reference made it apparent. Every astronaut who has described the experience of looking out the window from orbit has struggled to convey how different the visual experience is from any ground-based intuition about what being in space would look like. Earth fills a large fraction of the visual field. It is curved, visibly, from 400 kilometers. Its weather systems are visible as swirling white patterns against blue ocean and brown continent. The terminator, the boundary between day and night, moves slowly across its face. At the orbital velocity of 7.66 kilometers seconds, the spacecraft traverses a degree of latitude or longitude roughly every 13 seconds, making the motion of the ground beneath it visible in real time, not as a blurred impression, but as a clearly perceptible drift of geographical features. The object that dominates this view is not above or below in any felt sense. The astronaut floating at the window is neither above the Earth nor the Earth above them. The relationship is purely spatial. The spacecraft and the astronaut are in one place, the Earth is in another, and the direction between them is the direction their inner ears have no physical basis for labeling. The convention of calling the planet below, established by habitat labels and social convention, is honored but increasingly felt as arbitrary. The deeper cognitive shift is in the understanding of motion and direction. On Earth, horizontal motion along the surface is the easy kind of motion. Vertical motion, fighting gravity, is the hard kind. In orbit, this is reversed in a specific way. Moving along the orbit, the horizontal direction, requires essentially no propellant because the spacecraft is already moving at exactly the right speed to maintain the orbit. Moving perpendicular to the orbit, changing altitude, is the expensive maneuver because it requires changing the orbit's shape by adding or removing energy. The natural motion in orbit, the motion that costs nothing, is sideways. The shift in thinking required for orbital mechanics can be described as learning to think primarily in energy and momentum rather than in position and direction. On Earth, primary questions of navigation are where am I and which way do I need to go? In orbit, the primary questions are what is my velocity and what orbit am I in? Position matters only insofar as it determines which maneuver is currently most efficient. The when of a maneuver is often more important than the where in any geometric sense. Mission controllers at NASA's Johnson Space Center in Houston, when managing ISS operations, speak a language of delta V and orbital periods and phase angles that is essentially foreign to the position and direction intuitions that ground navigation uses. A maneuver is described not as going up or going forward, but as a prograde burn of such and such meters per second, which will raise the apopsis by such and such kilometers and change the orbital period by such and such seconds, resulting in a phasing that will bring the ISS into rendezvous position with an approaching vehicle at a specific future time. The entire description is in the language of energy and momentum and timing. Learning this language is part of what makes spaceflight engineering so different from aviation. A pilot flying an aircraft thinks primarily in terms of altitude, heading, and airspeed. An orbital engineer thinks primarily in terms of orbital energy, angular momentum, and timing. The connection between these two frameworks exists and can be translated, but the orbital framework is the more fundamental one for describing motion in the presence of gravity at any significant scale. The realization that space travel is primarily about going sideways rather than up changes the way you understand every aspect of the human relationship with space. From the engineering of rockets, to the biology of astronauts, to the trajectory planning of interplanetary missions, to the way the universe operates at every scale. It is one of those insights that, once understood, cannot be ununderstood. The images of rockets ascending vertically and spacecraft floating gracefully above a blue planet begin to carry completely different meaning than they did before. The difficulty of changing orbital energy, the extreme cost of the sideways velocity needed for orbit, explains immediately why access to space remains expensive, why the rocket equation is the fundamental constraint on all spaceflight, and why every incremental improvement in propulsion efficiency or structural mass fraction is so important. Barrier to space is not the ceiling of the atmosphere. The barrier is the energy required to move sideways fast enough that falling never intersects the ground. The absence of a universal up direction in space explains why long-duration spaceflight is physiologically demanding in the specific ways it is, why habitat design for future missions must grapple with novel orientation challenges, and why the intuitions that work perfectly on Earth's surface become unreliable guides in interplanetary space. The vestibular system and the proprioceptive system and the visual cortex were shaped by billions of years of evolution in a gravitational environment. Moving that evolved machinery into an environment where gravity is either absent or organized around a different massive body requires both physiological adaptation and cognitive flexibility that do not come automatically. The principle that everything in the universe is falling connects the orbital mechanics of the ISS to the behavior of galaxies, to the large-scale structure of the universe itself. Gravity is not something that holds some things down while other things are free. It is the universal organizer, the force that causes everything to accelerate toward everything else. And the structures we see, from the ISS's orbit to the Milky Way's spiral arms, are the stable configurations that arise when matter falls in sufficiently specific ways that the falling keeps repeating without intersecting. We never simply fly up because up is not where anything useful is. What is useful is speed, direction, the specific orbital configuration that keeps you falling in a closed curve rather than an open one that ends in the ground. The universe does not have an up. It has gravity, and everything in it, from the smallest spacecraft to the largest galaxy cluster, is working with that gravity, falling through it, orbiting within it, shaped by it. The rockets that carry humans to the ISS are not fighting that gravity to go up. They are using it, turning with it, building the sideways velocity that makes falling into orbit rather than into the ground. Is the whole trick, and it is extraordinary. The transition from the up-focused picture of space travel to the orbital mechanics picture represents one of the clearest examples of a conceptual shift that popular science education has not yet fully accomplished. The images and language that dominate public understanding of spaceflight, the rocket ascending, the astronaut floating above the blue planet, the spacecraft journeying to distant worlds, all encode the up intuition so thoroughly that the more accurate picture must be consciously learned rather than simply absorbed. This matters because the up intuition produces specific, predictable errors in thinking about space. It leads people to imagine that getting to space requires primarily a very powerful engine, rather than primarily an efficient one, that can sustain a long horizontal burn. Leads to the impression that weightlessness means absence of gravity, rather than free fall. Leads to the intuition that returning from the moon is a long downward journey, when it is actually a very precisely timed orbital maneuver that uses the moon's gravity and Earth's gravity in sequence. Each of these errors, when corrected, reveals something deep and real about how the universe is organized. The universe, as revealed by physics, has no preferred vertical. It has gravity, and gravity is what gives every place near a massive body its local up direction, while every place far from any massive body has no up direction at all. The structures of the universe are not layered vertically. They are organized radially around centers of mass, with orbiting populations at various distances moving at specific velocities that allow continuous falling without continuous arriving. The universe is full of things falling forever, not because they are trapped, but because falling in a closed orbit is the only stable long-term relationship that gravity allows between objects that do not collide. On one of those falling things, orbiting a star, which is orbiting a galactic center, which is participating in the large-scale flow of a universe, organized entirely by gravity and motion, and the absence of any direction called up.